What we'll do now is go through some fundamental systems engineering concepts. Now, I've said this subject is robotic systems design, and so there's some element of systems engineering and systems design that goes into the robots that we'll be creating. Now, we have a whole subject in our course, MS3 SYE, devoted to systems engineering, and we won't be going through all that subject, but we'll pick out a few key concepts and employ those in a very practical sense. Now, the basic premises of this are things like life cycles, looking at stakeholders, managing system at every step of the way, and looking at the requirements and developing a detailed requirements analysis. It's essentially creating a structured approach to engineering design. Now, the first one is a system life cycle, and this goes through several different stages. We start off with pre-acquisition, so this is where someone in the business has a particular idea and starts planning, could we solve this particular problem, could we automate this procedure? Then comes the acquisition stage, where you're looking at detailed requirements, you're looking at design, you're looking at actually producing the system. Then there's the utilization stage, where you're looking at actually using it to perform its prescribed task and supporting it, regular maintenance and things like that. And retirement, of course, where you sell it, you scrap it, you modify it for a different use, whatever it may be. Next concept is this one of managed design flow. And there's lots of paperwork to track and control these big projects, particularly when they are big projects. Looking at things like the business needs, the stakeholder needs, looking at a requirement specification to make sure you're actually building the right system. The allocated baseline, what are you actually going to build and what are you going to offer? And to what standard is that going to operate? Developing documentation for this and looking at the system acceptance of this. Within systems engineering, we cover all of these different paperworks and tracking and a whole lot more as well to ensure we develop quality systems that will last the distance. One of the important concepts is that of requirements analysis. We need to clearly work out and define and write down what the requirements of the system will be. It might be a great system, but it might be the wrong system that we actually built. What is it the business actually wants and needs, and what standards does it need to meet? For example, does it need to be waterproof, or can it be water resistant, or doesn't it matter at all? Will it never actually come into contact with water? These are important questions to ask, and it's important to ask these right at the start of the process. The further we get along the design process, the more expensive and more difficult it is to change and refine our requirements. The better we can bed down our requirements at the start, the better our typical development cycle normally will go. And one way that we can do this is with an RBS, or requirements breakdown structure. This is essentially a hierarchical list of requirements a system must meet. So at the top we have the overall project goal, or the mission of this particular project. And we normally have a sentence to state what that's going to be. We're going to create a robot to automate this process, whatever it is. And flowing from that, we have some key goals that will actually produce. So they might be goals related to its timeliness, or its overall cost, or its overall efficiency or uptime, or whatever it happens to be. And then with each of those, we have some key functions and features that make up the lower level requirements. And those all can be traced back to high level requirements and essentially point towards fulfilling that project goal or the mission. Let's look at an example. Here we have an example of a domestic security alarm system. And that's basically what it is. The mission is to produce a domestic security alarm. But look at the different goals of this. We want to deter unauthorized entry, we want to detect entry, we want to classify entry, report unauthorized entry, and provide a market-leading solution. And then each of those has a number of sub-requirements that will make it up. Things like, for example, so in our requirements breakdown structure, we have a whole lot of sub-requirements, like detecting unauthorized entry, recording that entry time and logging that entry time, recording failure rates and things like that. Whatever it may be, these requirements that we need to know should be specified. There's no point saying, oh yeah, we need to detect entry, and then at the end the person says, oh, hang on a sec, you detected entry but you didn't log the time and those sort of intervals. All those sort of requirements should be there right at the very start. So we go from looking at a requirements breakdown structure we have this top level mission requirement. It might be something like develop a domestic security system. It might be to develop a light aircraft. And then there's some goals based on what it needs to do, like deter entry, have a large capacity, have a fast turnaround time for our aircraft, whatever it may be. What are those goals? What are those key elements going to be behind our design? Well, then we have our work breakdown structure, a WBS. And previously we had our RBS, requirements breakdown structure. That was a hierarchical list of logical things that need to be performed, logical requirements. Here it's a hierarchical list of physical work, a physical list, not a logical list like our requirements breakdown structure. So what work is actually required to build our system? So for a house, for example, we need to put in the foundations, we need to put in walls, we need to put in doors, we need to wire electrical subsystems, we need to wire maybe security systems, we need to put in plumbing. All these things are work things. They're not logical things, i.e. there must be some way of entering into the house and it must be this sort of width. It's physical things of actually we need to install this door, we need to install this wall, we need to install this garage door, for example. Then we have functional flow block diagrams, or FFBDs. And this shows the interrelationship between functions performed by a system. These are fairly similar to some of the sort of things that we'd use when writing code and writing flow diagrams for our code. And it allows us to specify are things sequential, or can they operate in parallel? What are the different functions operate in? Are there alternate paths? And we might have a top level functional flow block diagram and then lower level ones for various parts within that functional flow block diagram. And this essentially consists of a number of boxes and arrows. Here's an example for an aircraft once again where the aircraft lands, it taxis, we need to do some things to turn it round, and then it taxis and takes off again. And turning it round, we might have a specified period, maybe 30 minutes or so. What things do we need to do, like unloading, refueling, cleaning, making safe, all those sort of things. So functional flow block diagrams give us that sort of structure and sequential analysis of what's going on.